the email contents. That's the mechanism actually used in pretty good privacy or email encryption technique. So based on this, I will move to the next slide to finding the background problem actually. So as I discussed that PGP uses hybrid crypto system, symmetric and asymmetric. Symmetric is AES and asymmetric is RSA. But the problem is that I told that PGP sended the key and the data together from sender to the receiver side. So we think that it is less secure still, because if the attacker can get hold access of it, then we may lose both the data and the key together. That is the concerning issue. Because of this, we plan to make this system more feasible by using the blockchain technology. So in the next slide, it has the details of the blockchain technology, that how our approaches actually tackle this issue. So two part. Number one, the off-chain and the on-chain part. So our contribution, as I told yesterday, I only discussed yesterday about the blockchain part, because the encrypted key, how efficiently stored from sender side to the receiver side using the blockchain technology, we consider this one as per the discussion of the previous class. Then why blockchain? Because no risk of lost data in enhanced security. Why no lost data? Because blockchain has some built-in characteristics that I described in yesterday's lecture, that immutability is one of them. So if we put any data in the blocks of the blockchain, so it is quite difficult to alter or change this data. So we want to use these characteristics or flexibility from the blockchain. For this, we want to add this blockchain technology while sharing the key from sender side to the receiver side. Then the another one that is related to this today's topics, the ECC. Where we implemented ECC actually. Actually, we implemented ECC in the off-chain platform. I mean, there is no blockchain in the off-chain platform, while encrypting the original random key using the receiver's public key. At the time, we used the ECC algorithm rather than RSA. Why ECC? I already described in the first few slides that the major concerning is the key length. So we think that if we replace RSA with the ECC, then the key size will be smaller. That will reduce the size of the encrypted key that we want to actually store in the blockchain. So that obviously will saving the blockchain storage. The next one is the less data to process. I mean, lower gas will be consumed if the payload is less, and the cheaper transaction fee. As the gas is directly related to the transaction cost, then the transaction fee will be less if we use the ECC algorithm rather than RSA. So moving to the next slide, it is the contribution, actually contribution of this today's paper, that key sharing mechanism using for the PGP system of email communication, but we will utilize the ECC, elliptic curve cryptography here. And at the same time, in the previous yesterday's lecture, I showed two papers, but still these two papers used for the single recipient system. I mean, one sender will send this key to one receiver like this. So today I will show the multi-recipient system. I mean, if I want to share one email contents to several recipients, then how I can share it or something like that. So this is the modification of the previous work actually that is applicable for email application, at the same time for multi-recipient system. So based on this, here I try to summarize the previous two papers. Although I discussed the finding of these two papers, that maybe if I consider the title, both the paper has the title of ECC. I mean, the previous two paper also integrated ECC, but yesterday I did not describe it because of the contents of today. For this, I'm focusing this one. But my considered point is both papers are based on ECC and blockchain, but these two papers is still usable for the single recipient system. I mean one-to-one communication or one-to-one sending this key from sender to the receiver side. Then in the next slide, I will try this paper, the paper 3 that I summarized here, that enhancing blockchain scalability for multi-recipient email communication using ECC. So in this paper, there will be blockchain, ECC, and at the same time, it will be effective for the multi-recipient system. So if I tell the motivation, what's the motivation of this paper, then I can tell, comparing previous two paper, that in previous two papers, sender only sent an email contents or the particular encrypted key to the one receiver. Then what is the drawbacks of this one? That the redundant encryption needed. So if I want to send 5 keys to the 5 recipient, then in the previous system, I had to encrypt it 5 times, then upload it, then sending. So no scalability support. For the multi-recipient system, that it is very common in modern communication that sending the same email contents to more than one user or multiple user. Because of this logic, that is the motivation of our this research, that how I can share these contents with the multiple recipient at the same times. Okay, to address this challenge, this study enhanced the existing blockchain-based PGP key distribution system to support multi-recipient. And what is the advantage of this multi-recipient? It needs single encryption. I mean, we can encrypt the contents or the key once, one time for the several recipient, and it will be highly scalable. It means support group communication. And for the identification of the particular recipient, we use here a new technique that is called the key ID. I will explain later about this one, the key ID mechanism to identify the recipient uniquely. Okay, so that was the motivation of this paper actually. Then if I go to the next slide, the proposed system, then the first slide, it is the slide of the registration phase. So it has several phases of this particular proposed system. So here it is showing the registration phase, how an entity can register within the system. So registering an entity first need to input some parameters of the entity like username, email, and the position. Then after that, the user can generate the ECC algorithm to get the public and private key. After that, the entity will make a request to the blockchain network to validate this user and add this user as a entity. So the blockchain network will scrutinize these parameters, and if it is matched, then it will be accepted and get the request notification back to the entity. And the key, the ECC algorithm, that one used by the entity, then the public key we will store in another place that will be public, that is called in the key. Everyone can see it and can get access of it. But the private key will be kept secret to the user or the entity. So that's the mechanism of the user registration in this system. The next one, it is the key ID actually that I told that in this system we will use in multi-recipient system. It is very difficult. The challenge is for multi-recipient system is to uniquely identify the designated receiver. It means if in a network has 50 entity or 50 user, then if one of the entity want to send the email contents, for example, 20, then how this user will identify 20 from this 50. So because of this key ID, actually concept count, we try to generate a unique ID for each receiver that will make each receiver uniquely identified. Okay, so how it is generated? At first, generated the key fingerprint from the public key that I show in the previous slide, that every entity will put their public key in the ring. So using this public key, we will use the SSA256 algorithm, then finding the key fingerprint first. After that, we will take the LSB of 64-bit, least significant 64-bit from this key fingerprint that we will use as a key ID. And every recipient compute it locally, actually. So there is an example, the lower part of the slide, it is showing an example that how it is generated actually. So if we take this public key, for example, this public key from the key ring, then after that we will use the SSA256 algorithm, then the key fingerprint will be like this. Then we plan to make it more shorter. Then we take the LSB 64-bit, the least significant 64-bit. Then we consider that this bit is the key ID of that particular receiver. Then what we did after we getting this key ID, we simply put it at the beginning of the encrypted key that we want to share actually. In yesterday, I also show that we actually want to store this encrypted key in the blocks of the blockchain. So this key ID is only for the identification of the receiver, the first 64-bit. The next will be the encrypted key. Then both together of this pattern like this, the red one and the green one, combining this, and it will be uploaded in the blocks of the blockchain. So that's the difference between the single recipient and the multi-recipient system for uploading the encrypted key in the blockchain. Okay, so if I consider some few advantages of this key ID, at first it is compact, that we only use the 64-bit to make it compact, and used for secure indexing. So the particular public key will be used for generating this particular key ID that will make it unique and enhance privacy, because key ID is pseudonymous and doesn't export public key or identity. So that will obviously enhance the privacy of the receiver. Okay, so that was the plan to generate the key ID first. Then next slide, I will show the proposed system overview or the diagram. So maybe if open it is like this, maybe little difficult to understand. Can Maya make it one by one? Okay, that's good. Okay, so maybe in this slide, it is the proposed system overview actually. So I will explain it in the two parts, the sender side and the receiver side. So this diagram is particularly very similar that I presented yesterday for the single recipient system. Then what is the modification? The blue part of the upper side, that is step 4, 5, and 6 for the multi-recipient system, because it is related to the key ID that is new for the multi-recipient. Next, and in the bottom part, we can see that this particular step 11 and 12, that is responsible for the multi-recipient. Other remaining part, it is similar as the previous, as the yesterday's discussion for the single recipient system. Next, so if I only describe the upper part, the sender side, then we can see that most of the same as the single recipient system, then the addition on this one. Okay, next. So I will explain now how it is work. The sender first generate the random key as well, like the previous one. Then this random key will be used to encrypt the email contents. Then after that, we will use the ECC algorithm to encrypt this email, to encrypt this key to get the encrypted key in step 3. Next, okay, step 3, the one it is generated in step 3, that is the target actually to share with the multi-recipient. So to identify only the appropriate recipient, the step 4, 5 and 6, generated key ID and adding this key ID at the beginning of the encrypted key that is generated in step 3. After that, it will be uploaded in the blocks of the blockchain, completing step 7 and 8. So in the next, in the bottom part, the receiver side, you can see the modification is only 11 and 12 steps. So here, what does the receiver will do? At first, we'll make the transaction request. Then when getting the access, then getting the random key from the blocks of the blockchain of this particular receiver that is shown in step 14. Next. Okay, so next, once getting the random key of the particular recipient from step 14, this random key actually will be used to encrypt the original email contents that I told in the yesterday also, that our plan is only to considering the key, not the original email contents. So original email contents will be sent like as PGP system. So getting this key from this blockchain system, using this one to decrypt the original PGP contents and read this. So that was the mechanism actually that we used for the multi-recipient system. Next. So now I will discuss about the implementation and the evaluation. For the implementation, the environment is quite similar like the yesterday's one, that we used the two particular environment here, off-chain and on-chain. In off-chain, Node.js, that is responsible to generating the key, encrypting the key, and decrypting the key. Why we make it in off-chain, as I told in yesterday also, to reduce the load in the blockchain network. And in the on-chain, we use as well as Truffle and the Ganas. That Truffle is the development platform where we write down the smart contract. And Ganas is the local blockchain where we can deploy and see the transaction live. Okay, and another one is the ECC crypto library that we used for this, using this ECC algorithm and making the variation of key length. Okay, next one. So now I will discuss about the evaluation and result for this multi-recipient system. So if we consider the three main aspects, here I will show the number one, the effects of number of receiver. It means, as I told, that in this particular proposal, the main idea was to vary the receiver. So how the number of receiver can affect the particular gas value and the storage requirement of this blockchain system. And another one is the correlation analysis. Correlation is something making the analysis between the receiver and key performance matrices like receiver and gas, receiver and storage, receiver and transaction cost, something like that. What is the correlation between them? And finally, the comparative analysis. I will compare the previous single recipient system and this proposed multi-recipient system comparison. Next slide. Okay, in this slide, maybe at first, I will discuss the effects of multi-receiver on smart contract operation. So in the right side of the slide, we can see that there were four basic operations that I discussed yesterday also in this particular Solidity code: register user, KE accessing, deployment, and KE uploading. So based on these four, the first two, registered user and KE accessing, has no effect of the receiver. Why? Because registered user only uses fixed parameter to register. For example, name, email ID, institution, like this. So if we increase the number of the receiver, it doesn't affect registered user function. Similarly, KE accessing, it also has no effect if we increase the number of the receiver, because one particular receiver will access one particular key, not all the key. So it will not affect the number of receivers if we increase. Then the remaining two, deployment and KE uploading, it has the direct connection with the receiver, because deployment means the overall size of the smart contract. So more user means more input, so it will be obviously vary. Then another one is KE uploading. So based on the user, we will upload how many. For example, we will upload 20 encrypted key at the same time, and the next we will upload 50 encrypted key at the same time. So if it is 20, then the storage, or if it is 50, then the storage will be different. So number of receiver directly affected this deployment and key uploading operation. Then how it is affected, I will show the graph, the right graph for the deployment operation. We can see the x-axis is the number of receiver. So in this research application, we consider 1 until 25 receiver and try to get the gas values for each caches. Then the y-axis, it is showing the gas value. So in the next, and the right side figure, it is showing the variation of gas values with respect to the receiver. So here we also vary the receiver from 1 to 25 and finding the corresponding gas values. Then if we consider these two figures, then for the deployment, we see that if we vary the key length from 32 until 64 byte, then the gas value will increase from 120 until 140%, if you only consider the key length. Then for the K uploading, this gas value increment can be 120 until 200% also. Then for the practicality, for the deployment operation, the highest gas value used, it is still 37.71%. It means when the number of user is 25, we consider the highest gas value in the number of user of 25. When the number of user will be 25, then the system will use only 37.71% gas value of the maximum block limit. And for the KE uploading operation, if the number of user is 25, then it will consume almost 36% gas values of the maximum block limit. So it's actually still maintain the practicality and the scalability as well for the multi-recipient system. Okay, the next slide. Okay, in this slide, I will describe the still the effect of multi-recipient in the memory size actually. So how the memory size also vary with respect to the several receiver, it also show from this figure. Then next, from this figure actually we see that the memory uses increasingly with the count of the receiver. Then from this slide we can also see that the highest maximum memory used, that is 30 to 45%, when the highest maximum memory used, it is only 1.15% when the number of user is 25. Then the another observation is the point 3, that if we fix the key size, here we vary 3 different key sizes. Actually, KE 32 bits, KE 48 bytes, and KE 64 bytes. So this variation is based on the ECC algorithm key length variation. We try to vary the ECC key length 3 times. Then the encrypted key also vary 3 different key size. So if we consider the fixed key size, then 30 to 40% gas will be increased from receiver 1 until 25, according to this slide. Okay, next one. This slide, I will describe about the correlation analysis. So correlation analysis, it is a crucial role in evaluating the scalability of the proposed system. So we try to find that how these parameters is correlated to each other. In the first very left figure for the deployment operation, we can see that the x-axis showing the number of receiver until 25 and y-axis is the gas values. Then the correlation y equal to 17843.68x plus something. It is the correlation equation actually. Then from this analysis, we can see that the correlation coefficient of determination, that is R square, the R square value is 0.9989. So this determination value, the maximum value of this determination is 1. So while it is more close to 1 than the fitting the parameters well, we can say that. So in this case, first case, it is 0.9989. And in the second middle figure, we can see for the K uploading, it is still 0.9998. And for the memory uses, we can see that 0.9989. So it is very close to 1 for the maximum value of the correlation. So we can say that the parameters that we use to analyze this multi-recipient system all are correlated very well, and we got a strong correlation that is greater than 0.998 for all. Then the system practicality, we also see that the system resource consumption is predictable and consistent. I mean, if we use this correlation equation, then we can make the system predictable from the first. For example, if our system needs 25 users, then if we change the value of x, then we will get the value of y. It means how many users and how many guests will be calculated according to this system. We can make it earlier predictable. That is very efficient for the multi-recipient system, because we want to design for multiple receiver. Then I have to know that how many receiver I can handle within this system. Because of this, we try to make the correlation analysis. Then the another one, next. Oh, this is the comparison actually single versus multi-recipient system. So the single recipient, it is the previous yesterday's 2 paper, 1 and 2. And the multi-recipient is the proposed this one system. So in the left side figure, it is showing the deployment operation. Then the dash line that is in the upper side, dash line, it is for the single recipient, and for the multi-recipient, it is showing the solid line. So why this gas value is too smaller when you considering the multi-recipient system? Because in single recipient system, every time need a new transaction to deploy. But for the multi-recipient system, deploy a separate contract for each recipient. So the contract will be deployed every time in single recipient system, while in multi-recipient system, deploy one contract to serve all recipients. So we need only one contract. Because of this, both the operation, deployment and KE uploading, the gas value is much lower when you considering the multi-recipient system. Then if we see the finding, we can see that single recipient curve for deployment operation, it is increased exponentially, but multi-recipient, it is nearly horizontal. And at the maximum number of recipient, like if the recipient is 25, then we can save actually 95% gas than comparing to the single recipient system. For KE uploading operation, this reduction can be until 30 to 45%. That is shown from the finding. Okay, so maybe that's the finding of this particular paper that is related to the multi-recipient email encryption system. So the conclusion is try to design a multi-recipient email encryption system that has the support of multiple ECC key length. We use here 256, 384, and 521 bits for the adjustable encryption strength. And for the finding, we get a very strong linear correlation between the recipient and the resource uses. So I think that's all from this today's presentation that I prepared for the present. Then I will be happy if there are any question or answer. Thank you.
Okay. Thank you so much, Dr. Hussein. And let's open the question and answer session. If there's anyone want to ask a questions, you can raise your hands, please. Okay. Anyone? Okay. Anyone? Do you have questions? Yeah. Yesterday, I see a lot of enthusiasm for from all of you guys. So many students asking questions. Today, you can also ask the questions. So, yeah, Dr. Hossein, this kind of research is, I don't know, maybe your laboratory main research topic in Okayama. So that's why I see the paper is many papers written by you and then Dr. Maya. But I don't see Pak Eko's name. Right? Yeah, is this some like kind of the research topic that uh, uh, developed by your laboratory in Okayama?
Oh, yes, it is particularly in our laboratory in Okayama University. It has several research groups.
Mhm.
So one of the group is the blockchain,
Blockchain.
like the blockchain. Yes, like the blockchain or the cybersecurity. That group is related to this one. So this research actually, at the beginning, we started all the students, including the international students also, started the research in the
Okay.
individual. Then sometimes we have the discussion of group. For example, in every one day in a week, we have a group discussion. It means, for example, the blockchain group will discuss together with the professor also, something like that. And the name or the joining the work, it is after submitting the first paper, we actually discuss it with our sensei that is it okay if we try to make some combined work also? I mean, the person working in the similar field. For example, my research is blockchain and email security.
Yeah.
And Dr. Maya's paper is related to the main part is Bhanet network, but it also has the blockchain integration of Bhanet. Because of this, the blockchain is common in both the research. So the professor also agreed this one when he told that we are the academician, both of us, then maybe in later we need that kind of collaboration also. So it will be effective for us if we can make some combined paper for the same topics or something like that. Because of this, wherever it is blockchain in my research or Dr. Maya's research in the Bhanet also, we try to execute that part combinedly. It is including some other students also. In some paper, you can find some other students also. The Japanese student that is also work in the blockchain platform. So that was our laboratory rules like this, that we can combinedly discuss also. And even if we contribute in one to another papers, then we can also put his or her name also in the final publication based on the contribution.
Oh yeah, yes. That's very nice. Yeah, hopefully we also can have cooperation between the research group and also in our faculty. So in our faculty, faculty of computer science, we also have a cybersecurity research group. Okay, there is someone that raised his hand. Fadli, so you can ask your question.
Apakah suara terdengar, Pak?
Terdengar, terdengar.
Kalau saya ngomong bahasa Indonesia nggak apa-apa ya, Pak?
Oh boleh, nanti saya terjemahkan. So people Fadli will ask in Indonesian, I will translate
Okay, it's okay.
to you. Okay.
Okay.
Ini saya cuma kepikiran pertanyaan random aja sih, Pak. Dari tadi kan tentang KID-nya itu kan diambilnya cuma 64 bit. Nah, itu kan lumayan pendek tuh 64 bit. Nah, kira-kira ada resiko nggak sih kalau ternyata tiba-tiba ada dua orang berbeda gitu ya, dapat nomor KID-nya itu sama gitu. Nah, kalau itu terjadi itu nanti yang nerima aslinya itu siapa sih, Pak? Gitu. Itu sih, Pak. Kepikiran aja tiba-tiba kan tadi 25 tuh bisa. Kalau misal KID-nya sama, gimana itu kan karena udah lebih dihematkan lagi itu sih, apa si KID-nya tadi. Makasih, Pak.
Okay. So Fadli's question is about the key ID. So the key ID's length is 64 bits. Is it correct, Dr. Hussein?
Oh yes, it is 64 bit.
yeah,
For research, we use it 64 bit.
64 bits. Isn't it too small? I mean, is there any possibilities that maybe two person or two entity have the same key ID because 64 bits maybe is too short, or it's not possible? In case there is two entities or two people or more have the same key IDs, so where the mail will goes to?
Okay. Okay, maybe I understand the question. Thank you for the question. So in this slide, I also explained it is correct. We used the key ID as a 64 bit. Okay, so for the generation of this key ID, the question, can it be same or something, that kind of thing. So yes, so I'm answering this one that in the slide, I show that how the key ID is generated. So every user at first generated his or her public and private key. Then using an ECC algorithm, then the public key that is put in a place called the key ring, and everyone can access or see it. And the private is secret. So this key ID actually come from the public key. At first, we take this public key. For example, user 1, it has the public key of 1. Then we take this public key. Then using the hash algorithm, SA256. Then we get the fingerprint. That is the mechanism of generating the key fingerprint actually. So from this particular public key, using SA256 algorithm, we got the key fingerprint. Then if it is SSA algorithm, then it cannot be revertible, reverse also in the hash, the properties of hash. From the properties of hash, we can see if it is, it cannot be revert also. So after getting this hash of key fingerprint, it is not actually 64 bit, it is more than this. So why we actually choose this one? To make our system more lightweight. That is the major issue actually. From yesterday also I told that we want to put it in the blocks of the blockchain. So every time we try to do it, we are considering the storage. And yesterday I told that the off-chain operation, we did all off-chain operation outside the blockchain to reduce the storage load. Then this key ID of 60 bit has the same planning to make it shorter, to make the system lighter, actually. Then how about the duplication? Duplication is not possible, I think, because every user has its own public and private key. At the beginning, they will generate it. So every public key is correspondent to that particular private key. So this public key is unique for every user, right? So if the public key is unique, then we use this public key to generate this key ID. So this key ID will be also unique because the properties of hash, we know that if we change a single bit also, then the output will be different. Because of this, although it is 64-bit, it will not be similar for two users based on their public key. Thank you. I think he understands, or if he has any other explanation, I can.
Yes, yes. So I think that 64-bit is long enough to generate a unique public key for everyone.
Oh, yes.
To 64 bits is, I don't know, that's a lot, a very large number, right? Okay. Yeah, thank you, Fadli, for the questions. Any other question? Okay. Yeah, someone is raised his hand. Atollah Nuzul. Okay, you can ask your question.
Okay, thank you for the opportunity. Am I audible?
Yes, we can hear you.
Okay, thanks. My question is, you just said in your presentation that you built the system with on-chain and off-chain architecture. And can you explain more about the role of on-chain in the system and the off-chain? And then how do you build one? Like for example, in the off-chain, do you build it by with Node.js from ground up, and then you inject the algorithm of ECC in it, something like that? I think that's enough.
Okay, thank you for the question. I understand this one. So yes, in the implementation environment slide, I show that in our research, we use two environment. It is correct, the off-chain and the on-chain. So if I answer like that why, then the first question answer session, I already told that why. Two, the first consideration is why we consider two. Because to reduce the load in the on-chain environment, that is in one line answer if you consider why. Then the second one, that what we did in off-chain and what we did in on-chain. So I will start from the off-chain first. In our research, I told the research is something that support to the PGP system of email communication. Then what is this? That in PGP system, the original email is sent by encrypted format. So this one is encrypted using asymmetric algorithm. Then the key is also encrypted using asymmetric algorithm. Then finally, it is sent from sender to the receiver side. So in this particular research, we used off-chain for this key generation. For example, to encrypt the original email contents, we need the random key. Then where we actually generated this random key, it is obviously in the off-chain platform that we designed to generate the random key. The another one, the next one, after generating random key, we encrypt the original email contents. This encryption using the AES algorithm, that is also in the off-chain environment. Then the next process is to encrypt the random key. Encrypted the random key. It is using the asymmetric algorithm. In PGP, uses RSA, but we proposed that we will use ECC. This encryption also in off-chain environment. So after getting this encrypted key, our plan to store this encrypted key only in the blockchain. Then the on-chain environment comes actually. After finishing these three, getting the encrypted key, then our plan to store this encrypted key to the blockchain. At that time, the on-chain environment comes. So in the blockchain solidity or the blockchain code, we interact this on-chain environment to the off-chain environment and collect only the particular output from the off-chain. That is the encrypted key. After collecting this, it is stored in the blocks of the blockchain as our proposed system diagram. And again, for the receiver side at first try to get access of it from the blockchain. It means on-chain. Then after getting the encrypted key, the receiver need to decrypt it again. Then where this decryption? Then this decryption, after getting the key from the blockchain, this decryption will be in the off-chain platform, like similar as sender did. So after getting this key, receiver will decrypt it, the key first. Then using this key, receiver will decrypt the original email contents. That is also in the off-chain platform. So only the particular key that we want to store in the blockchain and access from the receiver side, that part is related to blockchain and on-chain environment. The remaining procedure is in the off-chain environment in this proposed system. That's all. Maybe if you have need any more explanation, you can ask.
Okay. Athalanuzul,
Yeah.
already answer your question.
So about the second one, regarding how do you build the off-chain? Is it like you build it from ground up by Node.js and then inject the ECC algorithm?
Oh, yes. We build it in the Node.js, but for the algorithm, in the implementation slide, I show also that we use a particular library, EC-crypto library. So we used this library to utilize the ECC algorithm. I mean, we did not do anything of the ECC algorithm or did not generate the ECC algorithm. We use the features of ECC algorithm from this EC-crypto library and the Node.js platform.
Okay. Yeah. Any other question, or maybe you still have a question, Mas Athalanuzul?
Thank you for the explanation. I think that's very insightful.
Yes. Okay. Is there any other question? Okay. Muhammad Raga. You can ask your question.
Bertanya boleh pakai bahasa Indonesia?
Boleh, nanti saya terjemahkan. Oke.
Saya mau nanya, kan di slide tadi dijelasin kalau sistem ini tuh sukses buat menghemat biaya gas blockchain dan memorinya. Tapi gimana dengan waktu latensinya? Mengingat si transaksi di blockchain itu kan biasanya butuh waktu konfirmasi yang dinamis. Dan kadang juga di blockchain itu ada antrean dari transaksi-transaksi yang lain. Nah, apakah proses pengiriman key enkripsinya itu bakal terasa delay di sisi penerima atau bagaimana?
Okay. Yeah, I will translate the questions. So in your presentation, it was said that this system can reduce the I forget your question. Mengurangi apa, Mas?
Storage maybe.
Oh, yeah.
Storage.
Yeah,
Or...
reduce the storage. And his question is that what about the latency time, because in the blockchain, anytime we want to write the blockchain, it will takes confirmation. We have to wait for the confirmation from the all the nodes. So yeah, I just remember that your in your presentation that your approach will reduce the storage and also the gas fee, and then but what about the latency time? Because yeah, every time we want to write in the blockchains, it will takes time to waiting for the confirmation from all the nodes. Does this system also works on those issues, or yeah, what about that?
Okay, so thank you for the question. So maybe the first was is the storage size reduction or something. So if it is, I just show in the last slide about the comparison of the single and the multi. Actually, the single is my previous two papers also, and multi, this one is the next proposal also. So how this reduced in the multi-recipient system, if I tell in a few lines, actually, like for example, in single recipient system, 1 by 1 or something, that kind of sending the encrypted key for one sender to the one receiver or something like that. That in the multi-recipient, the concept was one sender sending several key at the same times, and the particular receiver will access it or something like that. So it is all about the transaction. For example, in single recipient system, if we share 20 keys, then we need to make 20 transactions, 20 separate transactions. It means every transaction has few operation. Like for example, the deployment operation, we have to do every time. Then that particular point we try to reduce in the multi-recipient system, that we will upload it 20 key at a time with a single transaction. And then the particular receiver will access it or something like that using the key ID. So we can see that 20 transaction in single recipient and multi-recipient is the only way single transaction. Although the 20 key is the large than the one key. It is one of the another consideration, but we no need to deploy it 20 times. So every deployment has some transaction guest or cost and the storage issue also. Because of this, in multi-recipient system, always it is showing that how it is reduced than the single, if we consider it is two from the single recipient system. That's the major parameter actually that is responsible to reduce the storage or the transaction cost in multi-recipient system compared to the single recipient system. That is one. Then another one is the maybe latency time.
Yes, latency time. Yes. Is it also maybe it takes a short times, or you
Okay.
also reduce that?
Okay. In this research, actually, that we use the Ethereum blockchain. Then maybe okay. So the time in the first two paper, when we use the single recipient also, we try to find out the response time or the transaction time that you told that every transaction needs some confirmation. And if it is busy also, it can be QE or something like that. So if the lower latency, it means the faster blockchain response, or the higher latency, it is the slower. So in the particular first two papers, we also try to get this latency time, calculate this latency time, but we failed at the time because, I don't know, because in the Ethereum blockchain, it has a particular response time that cannot be predict if the latency time is less than this one. So I exactly forget that what is the time, but when we try to utilize the first 1 and 2 paper, we actually consider this one, how if I finding the latency time. Because of using the Ethereum platform, we cannot able to do that at that time because the latency time was the less than the minimum can compute by the Ethereum platform. Maybe another platform, it can make it more shorter time explanation, or and because of this, maybe first two and the second one also, we didn't consider this latency time actually. So far I can remember, but I just forget about the exact time limit that can be measured by the Ethereum blockchain. Maybe if you search, then I can get it. Maybe 1 to 2 seconds. I see here, sometimes it is told 1 to 2 seconds or something like that. So in this proposed system, when you making the transaction, it was less than this time. Because of this, every time it is showing that it cannot be measured of this time actually. But maybe when the scenario or network will be brought, then at that time we can find it, the latency time, if it is more than the minimum latency time of the Ethereum, or if you use another platform also, we can find this latency time actually.
Yeah. Okay. Okay. Thank you so much. Okay. Is there any other questions? I think will be last questions before we move to quiz from Dr. Maya. Okay. Muhammad Rafa, you can ask your question.
Thank you for the opportunity. In your presentation, that you mentioned that ECC is more efficient than RSA in terms of memory usage.
Yes.
But can ECC algorithm always replace RSA in systems that are already using RSA at the first place?
Yes.
Oh, okay. So if I answer to the point, then I think it depends on. Exactly, I cannot say that can or cannot. It depends on. So where we want to utilize and what is the application area and what is our final target. It depends on this one. As you told that RSA is obviously a built-in and very effective algorithm all over the world also. In PGP system also, they use RSA, as you told that it is very well structured or well structured and worldwide usable algorithm also. But within this one also, in this particular proposal, while we targeting to using the blockchain technology and targeting to make the system lightweight, targeting to consider the less storage in the blocks. Because of this, in particular, this application, we propose the ECC one. But if you consider, can we replace in all over the case, I think it is not be feasible to answer directly can or not. It depends on if you consider your requirement or your target or your focusing point, then you can consider. Or if you think that RSA is still okay, if I consider some other parts, then you can go with RSA. It is obviously depends on the application area or the platform or what is your final target actually. But in this particular research, our final target was this. Because of this, we try to focus to make the key shorter. Because of this, the RSA introduction here rather than the ECC introduction here. Sorry, the ECC introduction here rather than RSA.
Okay. Okay. Yeah. Yeah, I think let's end the question and answer sessions. If there anyone of you that still want to ask Dr. Hussein, you can contact him by using an email, and I think Dr. Hussein will be very glad to answer your questions. Okay, let's continue to the next part of our session. That is the quiz. Okay, Dr. Maya, you can explain about the quiz.
Okay, thank you very much, Aswin. Maybe give me a chance. Then I'm sending the link for the quiz for all the participants, except participants from Poland. So for Poland already have our link, but this is for all. This link for all, especially from Brawijaya University and all the participants here. So you can click it first.
Mhm.
Then also, later I will start it. However, please keep in mind that during you do this quiz, so you cannot open other tab or other application. Otherwise, it will be terminated. Okay, maybe one time will be only warning, two times will be only warning. The third time will be terminated, then you cannot do again that quiz. Okay, so like that. Okay, maybe we can start it now together. I will start the exam. Okay, I'll start for all the class.
Okay, okay. Yes, so
Okay.
from the student from RYZEN University, you already familiar with using a safe exam browser, right, for the final exam or midterm exam. So this application, it works like a safe exam browser, so you cannot open another tabs or another application. But if you force to do that, it will give the warning. Yeah, just answer the questions.
Yes.
Okay. Dr. Maya, we can continue. I think the quiz is already open.
Okay. How many minutes, Pak? It will be 10 or 15?
I think yeah, it's about 10 minutes.
Oh,
Yeah.
okay. It means
Okay.
until 8:30.
Yeah. Okay, guys, you can answer the quiz.
Yes, maybe no need to open the Zoom also.
Okay. Okay.
For the participants.
Okay.
Okay.
Okay, guys. Yeah, let's wait for the about 10 minutes. Yeah.
Okay.
Okay.
So you are also from the research group of cybersecurity, Pak?
Yes, yes. Actually, our research group name is under the umbrella of computer networks. That computer network is very broad topic.
Information
Wait, what is the name, Pak Eko? I forget.
Information Centric Network.
Oh, Information Centric Networking.
Yeah.
ICN. Okay. But yeah, the ICN is very broad topic. Like we also have a group of the researcher in infrastructure, in a wireless network, in the core network itself, and also one of the sub research group is the cybersecurity. And yeah, I'm and also Pak Eko is a member of cybersecurity group. Okay. Yeah. What about in your university, Polban?
Yes, actually, me too. From the network research group. However, in the network, it has several parts of concentration
Yes,
also. Yes, like that. So maybe some of it concentrate about the routing protocol or something like that. And if me and my other friend is concentrating about the security part of the network like that.
Yeah. Yeah, maybe we can have a cooperation between RYZEN University and Polban in the future.
Yes.
And also
Yes,
with
I hope so.
people of yeah,
Yes.
we can have more cooperation in the future.
Yes, maybe starting with this paper for this VLP.
Oh,
Like that. So, then maybe we can continue again like that.
Okay.
Oh, yes, that's a very good proposal also. If we can continue some together research after that also.
Okay. Okay. Yeah. We can discuss that in the future. Okay. Okay. Let's
Yes.
wait for the student. Yeah, I think we have 7 minutes more, guys.
Bukan berarti actually me and Pak Eko is different laboratorium for this. We don't have any former paper together like that.
My laboratory is health system, bro.
Yeah.
I'm medical, bro.
Then also he is our senior, so not in the same
Oh,
years.
that's why you
Yeah.
didn't have a paper together with Paiko.
Yes, yes. When he go back, then I just come like
Yeah,
that.
yeah, that's why.
Yes. But me and Biplop in the coming in the same lab and same year also.
Yes.
So, how about Samsul Huda? Is it good? It's funny that Samsul Huda.
Good.
He's still there? Or come back to Indonesia?
I think it's still there, Mr.
Hmm.
Huda.
Yes, maybe still there with the girlfriend.
Oh, really? Whose
Yes, he
name?
has
Later.
later maybe it is recorded.
Yeah,
Oh,
yeah, yeah.
okay.
Yeah. Pak Eko tolong ya, Pak Eko ya.
Aman, Pak, aman.
Okay. Okay, let's wait the answer from the students. Yeah, yeah, maybe yeah, actually the participants is more than yesterday. It's 200 people here.
Oh, yes.
Yeah,
Oh,
I
amazing.
also asked my student from the cybersecurity course to join this lecture.
Amazing. Don't forget
Yeah, I
to
think
fill
yeah,
attendance.
the elliptic curve cryptography is related with our course because yeah, I remember that I explained about the symmetric encryption, asymmetric encryptions. Yeah, I think but actually I didn't explain about the elliptic curve because yeah the common implementation of the asymmetric encryption is using RSA. I think yeah, RSA is like I don't know more popular than the ECC, and yeah, I think this approach can like the questions I forget from who, but can ECC replace RSA? I think it's possible if you can provide uh, more sorry less computational cost because RSA is very heavy on computational cost. If SEC can build the lightweight systems, so I think maybe in the future we can also use ECC in as an alternative to RSA. Yeah.
Because maybe ECC more, I mean RSA more popular because it is more formal rather than ECC.
Yeah.
However, nowadays our sensei loves more to using ECC like that because it is lightweight also. Then yeah, maybe we can explain more.
Yeah, RSA is yeah very heavy and in computational cost.
Yes, as I
Like
told
for
this
example
also.
in yeah, like in HTTP, secure HTTP. Yeah. Wait, my connection is not stable. Okay.
Excuse me.
For example, in HTTP traffic, we cannot use RSA all the time. So the RSA is only used for the key exchange, because if all of the communication using RSA, the latency or the delay will be very long. I don't know. Is there anyone that already implement pure asymmetric encryption using ECC? So we can communicate all the time with the ECC, because I don't think it will be possible in RSA, because yeah, it takes a long time to encrypt the message in RSA. Yeah. Okay.
Maybe
Yes.
develop in this participant, there's a third will be fourth year student. So you have any idea for their thesis? Yeah, you can share maybe what the topic that can they bring to their thesis. We call it skripsi in here.
So as per the discussion, the blockchain technology and ECC, two key terms. So blockchain technology is also a vast area, and not so all topics, very recent topics also. If I tell my story, before going to Japan, maybe I don't have any knowledge about blockchain, because my bachelor and master's degree research, it was completely different. Then based on the laboratory requirement, as our laboratory is the information security laboratory.
We've gone away.
Some part similar to the security.
Develop your your video.
Maybe we can close your video instead, Viplov.
Finally, maybe I forget how many. It can be uncountable proposal rejection. Finally, he agreed to do my research in the blockchain. So the topics is new for me as well. And the people who learn about the blockchain also know that it is very new topics and has a vast area of the application. And maybe within few years, in the upcoming years, it will be applicable in many parts, I hope, including in many countries, including, like, for example, in my country, Bangladesh also. In my previous institution, I actually joined here recent. I previously worked in the Daffodil International University, is a private university of Bangladesh. So at that institution also, recently introduced blockchain technology for the students' interaction. I mean, the students' payment system, then the certificate, then the publishing result, that kind of things. They already integrated blockchain in one particular part. So I hope, like the whole world, maybe the countries like Bangladesh or Indonesia or some other countries also, the blockchain can have a very good impact in the upcoming years. So if the students want to do the research, particularly explaining or giving them some idea, I think it is difficult sometimes for me also, because I'm also new in this field. Then if the students feel interest, as you told that the third year and fourth year student, usually in Bangladesh, I don't know the system of Indonesia. In Bangladesh, usually third year and fourth year student has the project or the thesis in their mandatory course. So student must have to submit a project or even submit a research paper before they go from 4.1 to 4.2 or 3.2 to 4.1, something like that. So at that time, students actually focus for their research and thesis for the first time, I think. So if it is something similar to the Indonesian also in third year and fourth year, so I think the students who are interested to research in particularly the blockchain field, I think they can do. I think I can tell this one only that it has the great impact. It will have a great impact in the upcoming years from my last 3 years observation and continuing this one. So if the particular student has interest to research in blockchain also, and they need some idea or some conversation or some sharing knowledge with me also, I will be welcome to guide them or to suggest them about the available resource or about the research field or the application area or something like that. But particularly suggestion from me to what can they do, it is, I think, quite difficult sometimes. But students, those who feel interest in blockchain, particular this field, if you share the contract of me, I will share the contract here, at least the email address. So anyone can reach to me. So I will be available and happy also to assist.
Yes, thank you. Yeah, the
Okay.
system is similar in our undergraduate studies. So the student in the fourth year should have yeah, it can be a project or a research or doing research that lead to publications. But yeah, actually, like they have a final exam or final test or final project to do that. And actually, the blockchain topic is quite popular. I see a lot of a project proposal in national competition. So we have a national competition for undergraduate student, PKM gitu, Bu Maya. I see a lot of project proposal in our national competition. The topic is about the blockchain, and some of them wins the competitions. So actually, the blockchain topic is quite popular, and yeah, that's why I appreciate that you encourage the students to have the final project or the scriptsy in blockchain technologies. Yeah, like you said, maybe it will be very popular in the future. Okay. Yeah. Dr. Maya, I think it's already 15 minutes. So maybe you can share the results from
Okay,
our
I will
quiz.
share the result.
Yes.
But maybe before that, during I sharing my screen, then maybe Dr. Wibo can share also his contact, maybe
Contact.
if
Yes.
Yes, I already chat in the
Yes.
chat
Yeah.
box.
Yeah. So yeah, that's yeah, you can see it in the chat room, guys. The email from Dr. Hussein. So you can ask him if you have interest in blockchains and also the cryptography or maybe cybersecurity in general. Yeah. Okay, so yeah, this is the result.
This is the result for our participants. Okay.
Congratulations
Wow.
that
So
scored
good.
perfect. I think many of you have perfect results. Congratulations. Yeah.
Yes, congratulations. They can directly see the result also, how many percentage that they are correct when they finish. to submit like
Yeah,
this.
yeah.
Okay.
I know.
Maybe that's all. I will send the result to Mr. Eko.
Okay.
Okay.
Thank you so much,
Okay, thank you
Dr.
very
Maya.
much.
Okay, so I think that's all for today's session. Thank you once again to Dr. Hussein, Dr. Maya, Pak Eko, terima kasih banyak. Thank you so much for the students that already joined our guest lecture in today's session and also yesterday's sessions. Once again, thank you so much, Dr. Hussein. Hopefully that we can have another collaboration in the future.
Okay,
Okay.
thank you all also for giving me this opportunity. I try to share my previous experience to all of the students, and hopefully if they want to continue in this field, I can assist also in the future, or together we can make some collaboration in the future also. So thank you once again to the universities Brawijaya and the committee, the organizer of this program, the participant students.
Yeah. Yeah.
Please.
Sorry.
Yeah. Okay. Yeah. So we said thank you to the Polytechnic of Bandung, Polban.
Yes, thank you very much also for Universitas Brawijaya to give permission to us to join also this lecture from that is from Universitas Brawijaya and from Diplov also. So my student can have knowledge also about the blockchain and can know teachers from Universitas Brawijaya. Like that. Thank you very much.
Okay. So yeah, I think let's end this session.
Okay.
Thank you so much. Alhamdulillahirobbilalamin. Yeah. Good night and assalamualaikum warahmatullahi wabarakatuh. Bye bye.
Thank you.
Okay.
Yeah. Bye bye, Dr. Hussein.
Bye.